Hi everyone, in this video we are going to discuss this theorem. Okay, so this theorem is related with sequence in Rn. So sequence in Rn, that means it will have n number of components. That sequence is a convergent sequence and converges to point P, right? So P is also element of Rn, so obviously it will have n number of components. They have given sequence, this sequence converges to point P. We have to prove that each component sequence converges to corresponding component. So let us discuss in details. Okay, we are trying to understand the meaning of this statement and then we will prove this one, right? We have a sequence xk which converges to point P. Xk has n number of components, so xk1, xk2 second component, xk3 third component, and skn n component. So point P is an element of Rn, so obviously it will have n number of components. They have given this sequence converges to that point. So we have to prove that first component converges to the first component P1. Sequence in second component converges to point which is in second component. Third will converge to third component, and in this way nth component will converge to that Pn. So this thing we have to prove. Okay, so let us start to prove. First of all, I will write the given information. Okay, so I am writing here we have that sequence xk converges to point P, right? So I am going to follow the definition of convergent sequence. First of all, I will take epsilon greater than 0 be given. So definition of convergent sequence says for given epsilon there exists n belongs to set of natural number. Let us write, therefore there exists n belongs to set of natural number such that d of xk comma p less than epsilon for all k greater than or equal to capital N. Okay, by definition of convergent sequence I will write it. This is small k, let me write properly. Okay, but see this d is a Euclidean metric, Euclidean distance. Okay, so it is defined with the help of norm, so that's why I can write, therefore norm xk minus p less than epsilon. Okay, but what is xk? Having n number of components, so let me write therefore norm xk1, xk2 and so on xkn minus that point P has also n components, so that is p1, p2 and so on pn, which is less than epsilon. I should write this condition each and everywhere, getting? So let us continue here. So there is a subtraction. So all of you are familiar with how to do the subtraction. First component minus first component, second minus second, in this way. So let me write here norm xk1 minus p1, xk2 minus p2 and so on. Last component minus last component, that means xkn minus pn. This is less than epsilon. So all of you are familiar with the definition of norm, which is defined with the help of square root. So let me write here. So this is nothing but root of square of first component plus square of second component plus and so on square of n component minus pn square less than epsilon. Okay, actually I should carry this condition everywhere. At the end I am going to write it again since we don't have much space here, that's why. To remove the square root, I will take square of both sides. So if you square of both sides, you will have xk1 minus p1 square plus and so on xkn minus pn square less than epsilon by square. By taking square of both sides, we are adding all these squares and we are saying it is less than epsilon square. That means definitely each of them is less than epsilon square. So therefore xk1 minus p1 square less than epsilon square, xk2 minus p2 square less than epsilon square, and so on. For the nth component also we can write xkn minus pn square less than epsilon square, and this is true for all k greater than or equal to capital, and it is true for everywhere. Okay, I should write everywhere. So we are adding all these things. Squares are there, so obviously these are non-negative things, and their sum is less than epsilon square. So each of them, first one less than epsilon square, second is less than epsilon square, nth one is also less than epsilon square. There is no more space to write. Make a screenshot of it, then I will go further. Okay, so now what will I do? I will take positive square root of both sides. Okay, so therefore if you take positive square root, there will be mod xk1 minus p1 less than epsilon for all k greater than or equal to n. Here also mod xk2 minus p2 less than epsilon for all k greater than or equal to n. And for last one also, by taking positive square root of both sides, we will get xkn minus pn less than epsilon for all k greater than or equal to n. But see, mod is there, that means in R with usual distance, okay, with usual distance. So here this is a definition of convergent sequence. Okay, definition of convergent sequence, mod is there, that means we are talking about usual distance in R. So therefore we say xk1, this sequence converges to p1 in R du. Therefore that xk1 converges to p1 in R du, usual distance, since we have got mod there. Similarly here also xk2 converges to p2 in R du, and so on. For last one also we can write xkn converges to pn in R du. So in this way we proved that each component sequence converges to corresponding component. Getting? So in general they have mentioned xki converges to pi, and this is true for all I running from 1 to n. So in this way we proved this theorem. Okay, so make a screenshot of it. In next video we are going to discuss converse part of this theorem. Okay, thank you, see you.